Good day to you, and I am Jared Skeens. Welcome to the Zoom room. We are on our Trigonometry Part 4 in our series, and today we would like to look at the inverse trigonometric functions, the three basic inverse trigonometric functions. And again, we focus primarily on the Cambridge A-level curriculum from the Pure 1 math book. And in the formula sheet that Cambridge gives, they provide these 6 range statements. Now, if you remember from the functions unit, in the functions unit, we talked about domain and range of a function and the inverse function. So remember that inverse is the opposite of the regular function. So in basic math, add and subtract are opposites. Multiply and divide are opposites, opposite operations. Well, when we move into functions, the function and the inverse function also are opposites. So we learned that the inverse function can be designated with this little -1 exponent, but it's not really an exponent like in algebra. The -1 exponent in algebra would take like x to the -1 and it makes it 1 over x. That's not how it works as an inverse indicator. So this is simply the notation that it's the inverse tangent or the inverse cosine, the inverse sine, meaning it's the opposite of the regular functions. But what we learned in the functions unit still applies to inverse functions with trigonometry. But they give to us these range statements, okay? Now, remember when we talked again in the functions unit, the domain of the regular function becomes the range in the inverse function. They switch. Same thing with the range of the regular function becomes the domain of the inverse function. So we saw that with algebra, you would take, we had to find the inverse function, we had 2 rules. Switch x and y, solve for y. Basically the same thing applies, but you're not going to be really doing that with what we're covering today. Although there is a section that combines the two, there is a functions of trigonometry that takes what you learned in the functions unit and what you learned in the trigonometry unit, and it blended it together. So we might have a separate sharing session just for that. But what I want to cover today is how this inverse trig function works, or how to understand these range statements. So here we see on the top row are the range statements given with degrees, and we see our inverse sine function is between 90 and -90, and we see our inverse cosine function is between 0 and 180, and we see our inverse tangent function is also between 90 and -90. These are a little bit odd range statements from what we're used to. In the basic trig functions, our normal domain was like 0 to 360. So we want to look at why, when we did the basic trig functions, the normal was 0 to 360, but now when we get to the inverse, there's these kind of odd range statements. We see on the second row here that you have the same thing but in radians. So instead of -90 to 90, it's negative pi halves to pi halves, 0 to pi, and negative pi halves to pi halves again. And if we look at it, and we see the quadrants. Underneath each of these, I put the quadrant that it's referring to. So for inverse sine, and let me get this a little bit better here for you. So for inverse sine, we see that there is a first quadrant here, and we also see there's a fourth quadrant. Remember, all students take calculus, so sine is positive in the first and second, and it's negative in the third and fourth. So we have one positive quadrant and we have one negative quadrant. Now, why did they pick quadrant 4 and not quadrant 3? That's what we want to look at here a little bit. Then with cosine, we see 0 to 180, so we have a first quadrant and second quadrant. Again, with our all students take calculus, we have cosine is positive in the first, it's negative in the second. So again, we have one positive quadrant, one negative quadrant. And then with tangent, tangent actually has the same range statement as inverse. The inverse tangent has the same as inverse sine, with the exception of there's no equal signs in the inequality. And that's because, remember, tangent has a division in it and you can't divide by 0. And tangent is undefined at 90 and 270. So at 90 and 270 is the same thing as negative 90. You cannot have a tangent value, meaning you also aren't going to have the inverse tangent. And our inverse tangent is also first quadrant and fourth quadrant. So why are these numbers like positive and negatives, one positive, one negative quadrant? Just want to explain it to you a little bit. I know it takes a little bit of time, but it will help you when you get into the solving equations so that you understand what kind of values your calculator is giving to you and how you then can take that answer and find the ones that you need to fit the domain of your question. So here is an example. Now, fortunately with Cambridge, you do not have to graph the inverse function. Now, I've taken the liberty to go ahead and graph one of them. I'm not going to graph them all. Just use one as an illustration so that you can see why things happen both with your calculator and why to make sense of these range statements. So if you remember from our last session when we did the graphing of trigonometric function, we have y equals sine theta, and we saw that it went from 1 to -1 is our understood amplitude, and the normal domain was from 0 to 360. So if we want to find sine of 30 degrees, well, 30 degrees is about right here. And if we follow that up and over, well, yes, that's 1/2, okay? Sine of 30 degrees is 1/2. And we also know that based on our special triangles that we looked at the first in part 1. So sine of 30 equals 1/2. If you notice our 30 degrees right here, if we went down, there's no graph down here, meaning there's no solutions. And if we go up, there's only this one solution right here. If we go up, there's no more graph up there. So wherever I go on this 30-degree vertical line, I only intersect the graph in one place, meaning sine of 30 degrees only has one solution. So when you take the basic trig function of an angle, it has one and only one solution to it. So there's no problem with our original 3 trigonometric functions. When we want to go the other way, the opposite direction, we run into an interesting situation. So algebraically, this is what it would look like. If we want to get rid of the trig function, sine, then that means we have to do the inverse trig function. So just like if you want to get rid of a +3, you subtract 3. Well, to get rid of a sine, then you do the inverse sine. It's what cancels it out. And what you do to one side, you have to do to the other side. So the inverse sine of sine cancels, and now we have the inverse sine of 1/2. So we would think that the inverse sine of 1/2 now equals 30 degrees. Well, is that the case? Yes, but if we look at an inverse graph, y equals inverse sine of theta graph, we now have a different situation. Remember, your domain and range from the original function switch on the inverse function. So our 1 and -1, which was the range, now become the domain. So instead of being on the y-axis, it's now on the x-axis. So here's +1, here's -1. And our 0 to 360, which was on the x-axis, is now on the y-axis. It's going up. So if we ask this question again, what is the inverse sine of 1/2? Well, 1/2 is right here. Now, when I go up and down along this vertical line of 1/2, notice I get 1, 2, 3, 4. Actually, you get an infinite number of answers because this graph goes back and forth all the way up and all the way down, and you're going to continue running into more and more solutions for this. So yes, 30 is one of those solutions, but so is 150, and so on and so forth. It continues both in the positive direction as well as in the negative direction. So when you put sine 30 in your calculator, assuming you're not using your special triangle, it gives you one answer. When you put the inverse trig function into your calculator, well, you don't have room for an infinite number of answers to show up on your computer window. So what they do is they limit the range so that you only get one answer in your calculator, okay? So if you look at the graph, notice with sine, it's first and fourth. Why is it first and fourth? Well, if we looked at this direction, the first is down here in this section right here, and the fourth would be up here in this section up here. In other words, they're kind of far apart from each other, okay? So here's the fourth. This would be the area of that, and they're separated. But the fourth also occurs right next to it in the negative section. So this is also the fourth. So what they like to do is they like to keep the solution set next to each other. So we have first quadrant, that's the positive quadrant. We have fourth quadrant, it's the negative quadrant. But to get to that negative quadrant, instead of going up through quadrant 2, through quadrant 3, to get to the fourth quadrant, we just go the opposite direction. Remember your 0 degrees, if you rotate up, that's the positive way. And if you rotate down clockwise, that's the negative direction. So we can rotate up to the first quadrant. We can also rotate down into the fourth quadrant. That way we get one positive quadrant and one negative quadrant for sine. That way we only get one answer out of all the positives and if there's an answer in the negative, you would only get one out of all the negatives. Notice -1/2 would give you a -30 degrees. And you can see that on your calculator. If you take the inverse sine of a -1/2, so if you take the inverse sine of a -1/2, it gives you -30. You can see the -30. So sometimes students are a little confused why their calculator gives them a negative degree value. Well, it has to do with how these inverse functions work. So you're getting the 30 degrees, but in the fourth quadrant from the negative direction. So remember, we also talked about reference angles. So that 30 degrees then becomes your reference angle. So if you want, let's say, the third quadrant value, which is also negative, all you have to do is go 30 degrees from the 180, and you would get 210. So if you do sine of 210, you notice that you get your -1/2. See the -1/2? So, but if you do the inverse of -1/2, it does not give you 210, it gives you the -30. So you got to get used to the fact that when you use the inverse trig function, that is your 3 trig functions, but the shift trig function, meaning you're using the sine to the -1, cosine to the -1, and tangent to the -1, which are just above your keys there, that it will only give you one answer in these particular quadrants. These are called the principal values for these inverse trig function because there are many values. So it gives you the principal value. You then have to put it into the quadrant that is required by the question. So you got to look at the domain statement, because your inverse function is limited to only 2 quadrants, but the domain statement of your question might include all 4 quadrants. So you're going to have to adjust your thinking to what your calculator gives you to what's required. Also, some of these are in the negative direction, and your domain statement might be all in the positive direction, although sometimes they are in the negative direction as well. So you got to really pay attention to those domain statements and also understand why your calculator gives you what it does. Okay, so you can see here that these 2 quadrants are next to each other. That's why those are the ones listed. For cosine, remember cosine is positive in the first, negative in the second. So it's no problem. They're already next to each other. The first and second quadrant is already next to each other. I won't draw the graph. And then for tangent, it's first and third are positive. Okay, so for cosine, the first is positive, the second is negative. For tangent, the first is positive. Remember, they're all positive in the first, and it is negative in both the second and the fourth. But again, the first and the negative direction to the fourth quadrant are next to each other. So this is the reason why they, on some of these, it goes in the negative direction, because that fourth quadrant is right next to the first quadrant on the graph without having to go through the second and third quadrants and not have that separation between it. So it will be important for you when you get into the solving trigonometric equations. So when we have that sharing session, I will remind you of what we talked about here. So let me bring up for you now let's share screen here, and we'll look at some questions together. so that we can see this work here. I'm going to erase these graphs because you don't need them anymore. Like I said, you don't have to graph the inverse trig function, but you should understand why those range statements are what they are. So here you see you have an inverse, except now instead of looking at it graphically, we're dealing with it algebraically. So you have the inverse sine of 4x to the fourth plus x squared equals 1/6 pi. Notice it's in radians because of the pi. And we'll come back to the board here because I have it written here. Now we're supposed to solve this. This is one of the Cambridge questions that we have. So here you see our inverse function. Now this is not the inverse function at the end of the solving equation that I was talking about. This is an inverse function at the beginning of the equation, and our goal here is to solve for x. So we need to make that inverse function go away here. So to make this inverse function go away, we just do the opposite. And the opposite of the opposite is the normal. So to get rid of the inverse sign, we just sine both sides. So if we sine this side, cancels, leaving us with 4x to the fourth plus x squared equals sine of, this is pi 6. And you're like, oh, what's sine of pi 6? Well, you can do it on your calculator, but you shouldn't have to because this is one of your special triangle values. So remember, pi is the same as 180. 180 divided by 6 is 30. So this is sine of 30 degrees, and we just saw that as an example. Sine of 30 is 1/2. So this is 4x to the fourth plus x squared equals 1/2. Well, now we've left the trigonometric platform, and now we're in purely algebraic platform. So what happens when we have a fraction in an equation? Well, we want to clear the fractions because nobody likes to work with fractions. So we're going to multiply everything by 2. And so that's going to give us 8x to the fourth plus 2x squared equals 1, because the 2's over here cancel when we multiply it by this one. Then, because we have a polynomial, we get it all on one side, set it equal to 0. So we get 8x to the fourth plus 2x squared minus 1 equals 0. Now, Cambridge in the A-Levels series, they really like to correlate units. So unlike IGCSE, where you study say one topic, and usually the question on the test deals with the one topic. There's a few things they correlate, but most of the IGCSE is one question, one topic. In the A-level, there's a lot more correlation where it takes what you've learned from several units and ties it together. So this is another example. They start you off in this inverse trigonometric situation, and by the time you get down to here, if you remember from the quadratics unit, this is under what we discussed as reducible to a quadratic. A normal quadratic follows an x squared x and then constant. In other words, the exponents go 2, 1, 0. This is just double that. It's a multiple of the 2, 1, 0 exponent from a quadratic. So this is 4, 2, and 0. Okay, it's multiplied by 2. That means if it's a multiple, you can still treat it like a quadratic, and the key to your quadratic is this x squared. So you could use the quadratic formula, and instead of doing x equals, you'd have to do x squared equals. But we don't need to use the quadratic formula because this factors. And if we factor this, your factors of 8 are 1 and 8, 2 and 4, and your factors of 1 are just 1 and 1. And the subtraction means we have to subtract the two values to get a 2. Well, to subtract two values to get a 2, we just need 4 minus 2. So if we factor this, this becomes 4x squared and a 2x squared. And we want the 4 to be positive. We want a positive 4 minus 2. So remember how this works in your multiplication. So if you work backwards, you see your 8x to the 4th. You see your negative 1. And then in the middle, we have a negative 2x squared and a positive 4x squared. 4 minus the 2 gives you 2. So, and then this all equals 0. Just put it up there. Then our product to 0 property means that 4x squared minus 1 equals 0. 4x squared equals 1. X squared equals 1/4. And then when you square root both sides, don't forget that you have 2 roots. I won't take time to explain why there are 2 roots in a root, but actually trigonometry helps you. Trigonometry and complex numbers can help you understand why that is. And so you get x equals plus or minus 1/2. Over here with this one, we end up with 2x squared plus 1 equals 0. 2x squared equals negative 1. And x squared equals a negative 1/2. And when we try to square root both sides, technically you can, but you end up with imaginary numbers. And what we want are only the real values of this. So remember, maybe someone taught you at some point that the highest exponent in your equation is how many solutions you have. So there are 4 solutions. We came up with the 2 real ones. The other 2 are not real, so we're going to throw them out. We're not going to include that in our answer set. Those 2 happen to be imaginary numbers where you get complex conjugate pairs for it. So 4 solutions, 2 were real, 2 are complex numbers. We only want the real ones for now. And so our answer to this is x equals plus or minus 1/2. So here we started off in a trigonometric. We ended up with algebraic, but it's good review for our quadratics. It's also good review from our functions unit. Kind of blends it all together. Now let's go back to the next question. Go back to our share screen and going to go to the next one here. We have another one with, whoops, whoa, sorry about that. Kind of lost it there. Here we go. And I'll let you look at that, and I'm going to write it on the board real quick. I'll erase this other one. We have the negative sine of x minus 1 equals the negative tangent of 3. Here we have 2 inverse functions. Okay, we have 2 inverse functions in this problem. And that might throw you off a little bit. Well, which one do I get rid of? Do I get rid of the inverse sine, or do I get rid of the inverse tangent? Well, first, look for your variable. Your variable is what you're actually solving for. So our variable is right here. We want to get the x by itself. That means we're going to want to get rid of this inverse sine. Now, how does that work with this over here? Actually, you don't have to worry about this. There's no variable there, meaning this is already a numeric value. You could just plug it right into your calculator. It gives you a value. You don't really have to do that. You can let your calculator do all the work. So if you do sine of both sides, because we want to get rid of this, that cancels. So you end up with x minus 1 equals the sine of the inverse tangent of 3. And you're like, can we do that? Yes, we can, but you don't have to. Your calculator will do it for you. So if you do that in your calculator, or actually let's wait one more step. Let's get x by itself. All we have to do is add 1 to both sides. So now x equals sine of our inverse tangent of 3 plus 1. Now make sure your plus 1 is outside the parentheses, and it's all set up. You can just do it directly on your calculator. So you hit sine. Notice it gives you a parentheses. Then you hit your inverse tangent. So it also shows you the inverse tangent with another parenthesis where you put your 3. Don't forget to close the parenthesis on your 3. That's the argument for the inverse tangent function. Then we close the parenthesis again, so that makes closes the argument for the sine function, and then we can just put plus 1. We have everything that we see on the board on the calculator, and we just hit equals, and it gives you 1.95 to 3 significant figures. So x equals 1.95, and that's to 3 significant figures, which is what Cambridge usually wants for their answer. Okay, so again, here we had 2 of them. Kind of sometimes makes you wonder what to do. Look for your variable. That's the one you're isolating. So that means we have to get rid of this. When you look at this, there's no variable, meaning it's already a numeric value. You can let the calculator worry about figuring that out. Okay, so let's, now that we've done 2 inverse ones, I would like to go back and do these angle ones that I mentioned, I think, in the first, I think I mentioned them in our part 1. Okay, so given that an angle is obtuse, so remember we talked about that. So we have obtuse, and we have sine theta equals k. And it wants us to find, in terms of k, an expression for cosine theta, tan theta, and for sine of theta plus pi. Okay, so now that I've written that down, we'll come back here. And remember when we talked about angles, I introduced you to some vocabulary. Acute means from 0 degrees, we rotate between 0 and 90. Acute means less than 90, so that means we're in the first quadrant. If it says obtuse, like our problem does, it means you rotate more than 90, but less than 180. So between 90 and 180 is obtuse. And if it uses reflex angle, that means the outside angle. So the outside angle could cover 1, 2, 3 quadrants, or it could cover 1, 2, 3, and into the 4th quadrant. So if we measure a reflex from the 0, it would go into either 3rd or 4th quadrants, and you have to look at the additional information to know which one it is. So for this one, all I do is just draw my quadrants. Obtuse means I'm in the 2nd quadrant. See, here's obtuse from our 0. That's what makes it obtuse. Draw our triangle to the nearest x-axis. And notice that sine theta, and theta now is actually the reference angle. The reference angle is what we're working with. And so here's our theta is K. Now remember, sine is opposite over hypotenuse. So we want this to be a fraction. So to make it a fraction, just put it over 1. There's our fraction. So sine is opposite over hypotenuse. So from our reference angle, the opposite will be our K, and the hypotenuse will be 1. Now that we've established the sides of our triangle, this is like going back to Sekolah. Once we've established the sides, we can use the Pythagorean theorem to find the missing side. So we need to quickly do, well, we'll call this, I guess, x for right now. So x squared plus k squared equals 1 squared, which means x squared equals 1, which is 1 squared, minus k squared. And when we square root, we get the plus or minus. But because we're going in the negative direction, we want the minus. If we were going in this direction, we would want the positive root. So since we're on the negative side of the x-axis, we want our x to be negative. Okay, so this is our value for right here. So I'm going to erase the x and put this right here. Okay, so now I'm going to erase our algebraic work right here, and now we can answer our questions. Cosine theta. Well, cosine theta is adjacent over hypotenuse. So it's just a negative root 1 minus k squared over 1, but you don't really need the divide by 1. Same thing. And if you want tangent theta, it's opposite over adjacent. Opposite over adjacent from the Sekolah, Toa, tangent opposite over adjacent. So we get, I'll put the negative on top. So a negative k over root 1 minus k squared. So instead of leaving the negative in the denominator, I put it up in the numerator. It doesn't really matter top or bottom as long as it's in one of those places. Now we get to the sine theta plus pi. Well, pi is 180 degrees. So instead of facing theta, we need to go an additional 180 degrees, meaning we want to look at this from a little bit. Okay, we want to look at this from a little different perspective, and I just realized I forgot to put the parentheses here, which is actually important. So there are parentheses around this theta plus pi, so it's sine of theta, but moved another 180 degrees, meaning instead of it coming to here, it actually goes another, from here, another 180 degrees to over here. So it kind of flips to the opposite diagonal quadrant here. Okay, so here was our original theta, the obtuse angle. This is the reference angle that helps us figure out the side. But the original angle plus another pi, or another 180 degrees. So now we're facing over here, and my reference angle is inside the triangle. So notice, always make your triangle to the nearest x-axis. So now sine, these sides will be exactly the same. All it does is flip down. So my hypotenuse is still 1. Hypotenuse is still 1. This side is now flipped over this way. So now it's a positive 1 minus k squared. And the k is now going down, so it's now negative. So sine of this new angle over here, opposite over hypotenuse equals just negative k over 1 or negative k. So this is why it was important for you to learn about these vocabulary words, acute, obtuse, reflex, so that you can figure out these type of questions. These questions really determine how well you understand your quadrants with relationship to the trig functions and these vocabularies about angles. Okay, so we'll look at one more together. And here we go. Got one more here lined up for us. And we see it is a reflex angle this time. So I'm going to erase this one. And call it reflex angle. And it says cosine theta equals k. Says that 0 or k is between 0 and 1. And what are we supposed to do? We're supposed to get sine theta, tan theta. Then we're supposed to explain why sine 2 theta is negative for the domain 0, k, for k between 0 and 1. Okay, so why is sine 2 theta negative? Okay, so we're ready to look at that. Now, first, our key word, our vocabulary word, reflex. Remember, reflex means it will either be in the third or fourth quadrant. Okay, reflex angle means it will either be third or fourth quadrant. So I'm going to draw my little picture here with my quadrants. I know it will be down in one of these. So now I have to look at the additional information. Cosine theta equals k, and k is between 0 and 1, meaning k is positive. So if k is positive, that means our cosine is positive. And if cosine's positive, means it's facing in the direction towards our positive x-axis, because cosine corresponds to our x-axis. So if this is positive, then that means our angle, our reflex angle, is going into the fourth quadrant. Okay, so I draw it up to our nearest x-axis, and this is our theta. And again, cosine is adjacent over hypotenuse. So adjacent over hypotenuse makes this. And again, we need to do our algebra really quick. So if we call this x for now, we have k squared plus x squared equals 1 squared. X squared equals 1 minus k squared. X equals the square root of 1 minus k squared. And this time we want the positive, or no, sorry, this time we also want the negative one because it's going down. So our x is going to be the negative root 1 minus k squared, because it's going in the down direction, which is the negative direction. So we get rid of our little Pythagorean theorem. You should, if you're in trigonometry, you should already know the Pythagorean theorem. Okay, so sine theta equals opposite over hypotenuse. So a negative root 1 minus k squared. Tangent, opposite over adjacent. So negative root 1 minus k squared all over k. Okay, just Sekolah, pretty easy. Now explain why sine of 2 theta is negative. if we double our angle, okay, if we double our angle here, so when we double our angle, notice our original angle is from 0 around here into the fourth quadrant. The very beginning of the fourth quadrant is 270. So the minimum value that this can be is like, say, 271, 272. So if we double that, that gives us 540. And if we go around 540, we take away our 360, 540 minus 360, which is a complete circle, leaves us back at 180 minimum. So if we double the angle of our original fourth quadrant, whatever it is between 270 and 360, you double that, take away one complete circle, and when you end up, you're going to end up somewhere in the third quadrant. Okay, so for example, 300 doubled is 600. 600 minus 360 is 240, which is, sorry, 600 minus 360, yeah, 240. 240 is here in the third quadrant. So we're going to be here somewhere in the third quadrant. So if we're in the third quadrant, notice sine in the third quadrant is still negative. It's going down. So sine 2 theta is third quadrant, which sine is sine of that value still negative. Okay, so that's why sine of 2 theta is still negative, because when you double a fourth quadrant angle, you end up back in the third quadrant. Okay, so these are the type of questions that Cambridge will throw at you. They're not really the main type questions. The main type questions deal with identities and solving equations. So I'll have a separate sharing session for each of those, plus a session on the trig functions as functions and trigonometry. So combining that functions unit with the trig unit, kind of need to do a separate one just for that. Okay, so that ends our part 4 with inverse trig functions. Please pay attention to the details. Those details will help you work through your solving process for trigonometry. Thank you for listening, and see you next time in the Zoom room.